and then if we have time, so I'm going to go slow, and I'm going to just compute some examples of small homologies that, as I said before, for Hochschild and Lie algebras. All right, so what do I want to do? Right, so we'll need this anyways. Remember what a projective object was? This was the universal property of projective, is that you can lift surjections. So if you have some B, you have some C, and this guy is surjective, then this guy exists and is unique. Well, I keep saying exists and is unique. I think every time that I draw, exists and lifting. Yeah, whenever I say that it's unique, you should doubt it. Most often I'm wrong. So for every surjection like this, there's a lifting of this guy to this place, so that this diagram commutes. So now dualize this to get injectives. And this is the notion of an injective object in a category. Well, this is slightly restrictive. I'm using a 0 here, so I'm thinking in an abelian category. Try to guess what the notion of projective in general would be. But an injective object in an abelian category would be the same thing with the arrows turned around. So I'm going to have 0, B, C, and now this guy is going to be injective. I'm going to have a map from B to P, but now let me call it I to recall that this is going to be an injective object, and I'm going to require, well, I mean, of course, this guy. So I can always map from here to here. Well, let's just say that this guy exists and is unique. Exists and is not necessarily unique. So this is going to be a commutative diagram. So an object I satisfying this condition for every injection, you can find this map here. It's called injective. Okay. Now, let's go back to our category of our modules. I think I'm going to be, I'm going to be using, so most probably, well, I may be confusing left and right R modules in a second. But let's look at our category of R modules. And if you give me any I think this is fine. So let's say that you give me a module M. Then I'm going to construct M dual to be the set of homomorphisms of abelian groups in M and Q mod Z. So that's the Pontryagin eigendual of M. And notice that R acts here as well. So if you give me a phi here and an R here, then you can look at phi acted upon by R. Now R is acting on the right, not on the left. And evaluated at M, you define this guy to be phi of R acting on M. So M, I think I got it right. M is an R module on the left. So that's why I'm using this multiplication on the left here. And R is acting on phi on the right. And this gives you a good definition of a right R module structure on phi, on M star. So M star is in mod R. And of course, this thing here is a good functor. This is a functor. Namely, if you have a map from M to M prime, then you get the dual of this guy, and you get a map this way. Okay, so the transpose of, let's say that this map from M to M prime is F. I want to give you a map here of phi prime here. This should be an element in here. So therefore, this guy needs to be evaluated in elements in the module M. And I need to tell you what this guy is. And there's only one thing that I can do. Apply F to M. This is an element in M prime. And just take phi prime of that. Okay. So this is the definition of this object. Okay. So this says that the dual, the Pontryagin dual, that sends M to M star and that sends F to F star is a functor from R mod to mod R up. Now both are abelian categories, and this functor is exact. So this functor is exact. This is not entirely trivial, so let's check the only non-trivial example. The point here is that M is 0 if and only if M star is 0. Now, of course, one direction is obvious. If M is 0, then every morphism out of M is going to be 0. So if M is 0, M star is 0, that's trivial. On the other hand, we can look at what is M star star. Well, I've given you a definition of what the dual is for a left R module. It's clear that if I take a right R module, I can just repeat this construction. So, okay, so let's do that. So as a caveat here, if you have a right R module, let's say N, then you can define N star, again, the same formula as Hom in abelian groups of N to QZ, to Q mod Z. But now R acts on the left. And the action is really just the same. So if you give me an R here acting on some phi that is in an N star, this guy needs to take an N here, and you define this guy to be phi of N where R acts on the right. So this, I started with a left R module. This is a right R module. And then this double dual is a left R module again. So M and this double dual are left R modules. And also it's clear that this statement is also true. If N is 0, then clearly N star is 0. Same argument. Morphisms from 0 are 0. So what we have is a map from M to this double dual, which just takes M, and it needs to give me, well, an element in the dual of M dual. So it needs to give me something that maps phi. This phi is in M dual. And it needs to give me an element in Q mod Z. So this is going to be phi applied to M. And now this is an easy lemma. This guy is 0 for every phi. So the application that sends phi, this is 0, oops, for every phi in M dual, if and only if M is equal to 0. So that's the statement that the pairing between M dual and M to Q mod Z that sends phi to m is non-degenerate in that sense. Okay. So m is 0 if and only if m dual is 0. And it follows from this that if you have a map, now, well, I think I've used n as a right. So if you have an f like this, then f is injective, surjective, if and only if the transpose is surjective, injective. And that one of them is trivial at the level of sets, because transpose is just composition. And the other one requires this level. So you can check injectivity or surjectivity of a map by looking at injectivity or surjectivity of the dual map, of the transpose map. And, well, so now you know that taking duals preserves injection and preserves surjections. So it preserves the exact sequence on the left and on the right. And therefore, it preserves kernels and co-kernels, and therefore this statement that this functor is exact, which I didn't write. Oh, no, here it is. So this functor is exact. So it follows that the functor that sends m to m dual is exact. Okay. So what else do I need? Okay. All right. So this is the statement we want to analyze. Remember a little bit what we said about torsion. So R is my ring. M is going to be an R module on the left. N is an R module on the right. And I'm interested in computing these groups, Tor, R, N, and M. So, and these were the right functors. So if I put a star here of the tensor product functor. So I was using this symbol. And it doesn't matter we've already proven that it doesn't matter if I take the derived functor of taking the tensor product by n or taking the tensor product by m, it doesn't matter. And I can use a projective resolution of n or of m. With this, we've proven already that it doesn't matter which one we choose. These homology groups are the same. All right? So let's recall why the name torsion for these groups. Why are these guys called torsion groups? And this came from the following observation. I could take R to be Z. I could take, well, I guess I'm using N to be Z mod P, Z, which is the Z module. And then M to be an arbitrary abelian group, which is an arbitrary Z module. Then I could resolve I could resolve N by looking at this resolution. R maps to R. Here is multiplication by P maps to N. So this is a projective resolution. This is a free resolution of N as an R module. Here is multiplication by P. And therefore, to compute the torsion subgroups, the torsion groups over R of NM, what I need to do is look at this. The first step is I look at this resolution, and I tensor it with M. So I have this resolution, and I tensor it with M, and take the homology of that. So now this guy here looks like R, M, and here's multiplication by P. This is in degree 0, this is in degree 1, and I've gotten tor 0 and M is equal to M divided by PM, and tor 1 and M, this is equal to MP, which is the kernel of this map, which are all the elements in M such that P times M is equal to 0, and tor N and M is equal to 0 whenever N is bigger or equal than 0. More generally, we spent a great deal of time in our last lecture to prove that homology in some circumstances commutes with arbitrary filtered co-limits, which was this case. And so let's say that N, instead of being this Z mod PZ, is a finitely generated abelian group. Well, then in that case, N is just a direct sum of a bunch of ZPIs and a direct sum of a bunch of copies of Z. So I can just put Z to the R. So that's because every finitely generated abelian group is of this form. And then again, this, of course, when I put N to be 0, if I put N to be Z, tor, well, again, tor 0, Zm, well, what is that, right? Well, I'm taking this, the torsion subgroup. The torsion group is a right exact functor. So this is the same thing as taking M tensor with Z over Z, which is just M. And tor 1, Zm, is already 0 because Z is free. It's projective as a Z module. So tor N, Zm, is equal to 0 for every N bigger or equal than 1. So what I see is that since tor is a homology functor, it commutes with finite sums. More generally, we've already proven that it commutes with filtered colimits. In particular, it commutes with finite sums. Then tor N, Z, and M is a direct sum of tors for each one of these guys. In particular, is 0 for every N bigger or equal than 2. Because it is 0 for each one of the summands, and it's 0 for each one of these free ones. And tor 1 is going to be just the direct sum of all the pi torsion of M for each M. Okay. So that's one thing we have. Another one we can do is, I claim the following. Let's say that, so you have now R is a ring, and you have N a well, let's take N. Let's take M to be Q divided by Z. No, let's stick to Z. R is, let's stick to R to be still Z. So I want to understand this guy as a Z, as an abelian group, as a Z module. So now, lemma, if n is torsion free, if and only if the torsion of n, oops, and this follows from the previous lemma because we can just take n. Oh, this follows from the previous lemma and the fact that n, the torsion, commutes, which we proved in the previous lecture with filtered colimits. And you can write any module is the limit, is a colimit of its finitely generated submodules. And we've already proven for the finitely generated submodule. That's it. Okay, so all right, so torsion-free modules are exact, are acyclic for the torsion homology. You take the torsion of n with anything is 0 for higher n, not for n is equal to 0. For n is equal to 0, we know that it's just the tensor product of the two modules. All right, so that's going to be our definition. So what we've proven, since we can compute this guy, since we compute tor n dot using a projective resolution of n, then what we know is that tor n p dot is equal to 0 for every n bigger than 0 if p is projective. P itself is a resolution of itself. So in degree 0, we get P tensor with whatever that dot is. And in degree 1, it's already 0. So definition, n is flat. Now it's for an arbitrary ring and an arbitrary module. So R is a ring. N is a right R module. And the same definition, of course, works for left R modules. But for an arbitrary ring and an arbitrary module, then this guy is flat if this happens. If tor n dot n is equal to 0 for every n bigger or equal than 0. I'm sorry, for every n bigger than 0. So bigger or equal than 1. And this statement says that projective modules are flat. And of course, I mean, if you take left are modules, same definition, just that tor dot m is going to be 0 for n bigger than 0, and then the projective modules are also flat in that category. Okay, so a nice exercise. Check that n is flat. If and only if you replace tor n by tor 1. I mean, of course, one direction is obvious, but then the other one is not entirely trivial. Okay. Now, why did I talk about injectives and why I'm now talking about flat morphisms, flat objects? First of all, and I talked about duals also. So the following statement is absolutely trivial. I dualized everything to go from projectives to injectives. I've taken a category and I've dualized the arrows. So clearly, if P is projective, let's say that P is a projective R module, then P star, which is a right module, by definition, is injective. This was the exactness of taking duals. So this is the exactness of the functor that is a Pontryagin dual of our modules. Indeed, so P being projective means that for any surjection here, BC, this guy exists. So what this is saying is that the map from hom PB to hom PC, that this map here is surjective. I can lift any guy here to a guy here. Okay? So in general, hom preserves, so this is for every surjection B to C. Hom preserves injection, but does not preserve surjections. It's left exact, but not necessarily right exact. So when it's also right exact, then P is projective. Okay, but if you have this situation, let's put names to this guy. So let's say that this was probably pi for this guy. Then let's say that this is I, and this is the one that I claim exists. Well, then if I look at C star, P star, I star, and well, pi star is a map from C star to B star, which is well, yeah, which is the transpose of pi, and then the transpose of this arrow is going to be this arrow. I am lying because if I put an arbitrary injection, so now this is injective because pi is surjective. So if I put an arbitrary injection, then I need to tell you that it is the dual of a surjection. And at no point I've said that the double dual is isomorphic to the original module. Okay? So this becomes true. So now this will become true, that every guy is of this form, if I put some finiteness condition. So what I mean by true here is the statement that every morphism here is the dual of a morphism there. Finiteness condition. So let's talk about those finiteness conditions. But let's prove something more general. Let's just prove that the dual of a flat module is injective. Just stronger than just proving it for a projective. So theorem M is flat if and only if M dual is injective. In particular, we've seen that M is projective implies M is flat. And so the dual is injective. Okay, so I think I've taken the time to state this here. This is the property, the fact that this Hom is projective, is still surjective, is the property that P is projective. Of course, injections can be stated in the same way. So what is the datum that M star is injective? Then again, this is for any injection, let's say from B to C, an injection, and a map to M star, then I want this guy to exist. Now, this is a map Hom B M star. This guy is Hom C M star. And of course, I mean, Hom is contravariant in the first argument. So if you give me a map from Hom C to M star, you get a map by composition to Hom B to M star, which is this map, is the composition with this. And what we want is that any guy here can be lifted here, so we still want that this guy is surjective. Okay? So this is surjective if and only if M star is injective. But M star was Hom itself. So this guy here is Hom from B to the R module that is Hom M Q mod Z. And the same thing here. This is Hom from C to the R module that is Hom M Q mod Z. And we've checked that Hom is adjoint to tensor. So this is abelian groups. So this is the same thing as Hom V tensor M to Q mod Z. And this is the same as Hom C tensor M to Q mod Z. And I want this to be surjective. So this is surjective if and only if M star is injected. Now, this is Hom in the category of abelian groups again. Hom in the category of abelian groups. And this is, by definition, C tensor M dual. And this is, by definition, B tensor M dual. And I want this to be surjective. And taking duals is exact. So that's an if and only if C tensor M, sorry. When I take the transpose of this map, this is B tensor M to C tensor M. Now it's injective. And this is if and only if M is flat. Tensoring with M always preserves surjections. It's a right exact functor. But it doesn't necessarily preserve the injection. So this preserves injection. This is an arbitrary injection that we started from B to C. So this is if and only if M is flat. Okay, so that's a good way of producing injective objects. Whenever you have a flat module, the dual is an injective object. It sort of makes sense. So in the world of geometry, this is the statement that if you have, say, a vector bundle, or you have a nice vibration, then just the huge space of étale sections. So this is just arbitrary sections from the base space to your fiber. That's an injective object. And that's the thing that you use. This is a huge space that you use to construct injective resolutions in geometry. So that's precisely this statement. You started with something that was nice. Being flat is a nice structure. I've told you about projectives. In particular, vector bundles are such a thing. And this thing is a huge object. These are morphisms from this nice, could be finitely generated projective object to this beast, which is Q mod Z. So this thing is a huge beast. But okay, but it exists and it's injective. Okay, so a slightly nicer equivalence, and then we'll essentially finish there, is the following. So we have the following criteria. Well, let's say that M is flat. And let's take an ideal inside of R. So this, remember, this is a module on the right. I think I was taking it, well, it doesn't matter. I mean, if M was on the right, then these guys were on the left, because everything here is in the category of left R module. And if M was in the left, then B and C are in the right, and then this is in the category of right R modules, and everything stays the same. Okay, so, but now it's going to make a difference, so let's pick one of them. I'm going to take M to be in the category of left modules, because I think this is what the book does, but I'm not really sure. It doesn't matter. In any case, just change left by right, and it should be what the book does. So let's take M an R module, so it's a left module. And let's say that it's flat as an R module. And let's take I inside of R as a right ideal. So switch left and right here, and the same argument works. So you always have this guy as a tensor product over Z, and oops, that's bad. That doesn't make any sense. So this is a tensor product over Z. It's not over R. And it surjects to the tensor product over R. Remember that this was defined to be the quotient of this space by this relation. So this guy was the quotient of this by a relation where the relation was that I tensor Rm, you declare it to be the same as IR tensor M. But you also have a map to Im, which is inside of M. So what is this map? This map sends I tensor M to I times M. I is an element of the ideal, which is an element of the ring. So you can act by I on M. And notice that IR tensor M would map to IRM, while I tensor Rm maps to the same thing. So this is well defined in this quotient. Okay? In other words, I have a map from here to M. Right? So this is just the definition is the image of this map. It's called this, and it's inside of M. And this guy factors through this quotient. So this map here factors through this quotient. But now what I claim is that this guy here is equal, and this is not true in general, but since M is flat, this is going to be equal. This is true. And this is going to be equal to finite sums of the form ij times mj. So, oh, sorry. That this is equal to that. Of course, this by definition is this. But this one is not. Okay. So in other words, I'm saying that this guy is an isomorphism, or in other words, I'm saying that the kernel of this map is exactly this relation that I'm modding out. Okay. And this is the flatness of M that gives us that. All right, so let's play again with this. Let's look at this sequence. Of R modules. Now these are R modules on the left because I was a right ideal. So R acts there on the left. And let's tensor this thing with M. Okay, for an arbitrary module M. So if I tensor this with M, I'm going to get, well, this is a left R module, and M, did I do this wrong? Wait. I cannot tensor them over M, over R with M. So what did I do wrong? Am I getting the wrong place where R acts? I think I might have screwed up left and right. Let me just fix this. But let me tell you what I want to get, because it's easy. So R mod I, let's suppose that R is commutative so that left and right is not a problem, and then we'll fix it together. But R mod I tensor with M should be M mod IM. R tensor with M should be just M, tensoring over R. Now this guy here, well, this is I tensor with M. I'm just saying that. Okay. So this one I do not know how to compute, so okay, so that's what it is. Now the next one should be Tor 1 of my M with R mod I. Max there. And the next one should be Tor 1 of R. But R is free as an R module, so this should be 0. So now let's fix this, because if M is a left R module, I should be tensoring over R with a right R module. And I don't see how R acts. Oh, no, of course, yeah. I is a right ideal. So I is a right ideal. R acts on the right on I. That's being a right ideal. That if I multiply by I times R, is inside of I. So I acts on the right on R. So R acts on the right here, and R acts on the right here. Okay, so I get this sequence for free. But now, so this is for a general module. I've never used flatness of M. I've used flatness of R, which is free, therefore projective over R. Okay? So what I see immediately from here is that if this guy is 0, this implies that, well, the kernel of this map is always the tensor product over R. This implies that IM is equal to I tensor R, which is what I wanted to prove. Because the kernel of this map is always IM. This is the quotient by IM. And here I have this I tensor over R. This was the tensor product over R. I'm taking Tor over the ring R. Okay? So the kernel here is always IM. So when this guy is 0, this sequence becomes exact, and this guy has to be equal to this, which is always the kernel. Okay, so M being flat implies this. Okay. Now I want the converse. Let's suppose that IM is equal to that. Then this Tor 1 is 0. How do I infer that M is flat? Okay, so to get the converse, so I claim that what I've proven is that M is flat implies this identity, that these two are isomorphic. So now I claim the opposite. I claim that if these two guys are isomorphic, then M is flat. And for that, I'll use this isomorphism here, that M is flat if and only if this guy is injective. So I'm going to prove that this guy is injective. And for that, I need a lemma. So again, I think I have it there, and I don't want to change names. So I have there a definition of what does it mean to be injective. No, yeah. So here's the definition of M star being injective. Means that these hums are surjective for every injection of B to C. So again, for every injection from B to C, F is flat. No, sorry, I is injective. If and only if hum from C to I is surjective into hum from B to I. So this is not the lemma. So that's the definition of I being injective. So now the lemma is that I is injective if and only if this holds for every ideal B inside of C, which is the ring R. So that's a particular case of this. Instead of taking an arbitrary injection of modules, then you just need to take an ideal, an arbitrary ideal. And again, I'm being sloppy here. If we're talking about right R modules, then this should be an arbitrary right ideal. And if we're talking about arbitrary left R modules, this should be an arbitrary left ideal of the ring. Okay? So I'm very bad with names. I suppose this is Bayer's extensions lemma or Bayer's. But it has a name, this lemma. So whatever, Bayer's criterion. Or whatever word was this, which I'm very bad at to remember. But like, okay, so let's prove this lemma. I mean, of course, one direction is obvious. Right? So if it holds for arbitrary modules, then it's going to hold for ideals. So now we need to check that if it holds for ideals, then it holds for arbitrary modules. And this is non-trivial enough that it requires the zones lemma. Okay, so let's suppose that this star holds for an arbitrary ideal. Now I want to prove that it's going to hold for arbitrary modules. So let's suppose that you have an injection of modules, B to C. And let's suppose that this map is not surjective. So you have some phi in here that does not extend. Well, I can put it here. So you have some phi from B to I that does not extend to the whole of C. Let's suppose that this guy does not exist. This we want to prove that is absurd. Okay, but we can look at some extensions. So we know that this extends up to some submodule that is in the middle between these two. So there is some B prime here, which is still inside of C. And suppose that this guy extends. So the set of all such extensions is a poset. Okay? So we're going to construct a category. Well, we don't need to talk about categories. So the set of all possible extensions like this is partially ordered. Because I can say that B prime is less than B second prime if it's included. So if I have this situation where I can extend from B to B prime, and I can further extend to B second prime, then this is a chain. I would say that this is smaller or equal than that. I can compare any two extensions like that, whether or not they're included. Okay? And now Zorn's lemma tells me that there's a maximal extension. So the trick again is that all of these inclusions are always inside of a big given universe, which is C. So Zorn's lemma, there exists a maximal extension. So let's call that extension B bar. So we have our B, which is inside B bar, which is inside of C. And actually, these two are not equal, because I've claimed that I cannot extend to C. And my original phi to I extends to phi bar here, but it does not extend to the whole of C. Okay? So now, what we're going to do is we're going to cook up. So I would want to cook up an ideal in R given this datum. Okay? So I know that there's an element C here in C that is not in B bar. So how does this go? I'd like to cook up an ideal of the ring, which I would want to prove that it's non-trivial. And I will want to extend this B bar by that. So let me just check what it is. Yeah, so I think that the obvious construction is just pick every element of the ring that sends C to B bar. So let's just pick, let's just define, I guess I've used I, to be the set of elements R in the ring such that RC is inside of B bar. Okay, so if I have two guys here, then their sum multiplied by C is also in B bar because it's closed under multiplication, under sums. And if I have R and S in this guy, then, oops, no, yes. So if I have R in R, and let's say S here, then S times R on C is equal to CS R, and this guy here is in B bar. So this guy here is also in B bar. So this means that SR is in this set. So this guy is a right idea. Okay. All right, so I have this right ideal, and I want to use the fact that we have this map, right? So I need a map from I to this guy. How do I construct that? So I will want a map from this guy to this set. Oops. How do I do that? Well, I can always do this. If you give me an element in here, I want a map from here to I. Let's say that you have an element here. Then what you can do is apply it to C, which is in B bar, and now you can apply phi bar. So that's a map from this to this. And let's check that this is an R module map. Okay? So if I multiply here by R, then this goes to this, but this is the same as C, I, R. And phi bar was a morphism of modules. So this is the same thing as phi bar of C, I, R. So this is a good map of modules. Okay, so I have this map of modules. And by assumption, I can extend maps from ideals to the whole ring. So this means that there exists an extension of this guy to the whole ring R to I that extends this guy. Okay? Okay, so now what we get is that you can look at B bar and add that extension. And add just the R module generated by C, by this action. Actually, I'm acting on the right. So here, this means the collection of all elements that are of the form R times an element in times this C. Okay? So this guy here is inside of C. Is strictly larger than this guy because C is inside of here and it's not in B bar. And my whole morphism phi bar extends here. So this guy comes with a map to I, which is phi bar on B bar. And it is this extension that was given by assumption on this component. Okay? Probably this is the wrong thing to do to take direct sum because that I do not know if it's direct, but it's a sum. Okay, but in any case, this is a larger extension of phi, which I assumed it was maximal. So this is absurd. Okay. All right, so this proves that we can check that a module is injective, but only checking that you can extend ideals. And that's going to play a game in here. Well, I said I was going to talk about like small examples of Hodgson homology, but it's certainly not going to happen. Just going too slow. All right. Yeah, I guess that's fine. All right, so the next ingredient I want to use is the following. We've already used this. We've already used that. I think it was of this form. I was looking at maps from B to M star, and I've said that this was the same thing as looking at B tensor M star, and this was the Hom tensor adjunction, right? Because this guy here is a Hom to Q mod Z. Okay, so let's do this in the case where B is an ideal inside of the ring. So let's take an ideal inside of the ring R. Okay. So we have this thing which is I tensor M star, and I have R tensor M star. And again, the M is going to be, M star is injective if and only if this map is surjective. But this is M star. And, well, what I wanted to prove is that I've already proven that M being flat, namely this guy being injective, implies that this is I times M. Now I want to prove it the other way around. So this is, well, I want to check that this guy, when this guy is surjective, but this happens if this map is injective. And the kernel of this map, we've seen that it was this thing of the ideal. So this guy is injective if and only if this guy is IM, because this is inside of him. The map from here to M factors through the kernel to I times M. Okay, so this guy is equal to that, implies that this map is injective, therefore that this map is injective, therefore that this map is surjective, and we only got the surjection for an ideal inside of R. Okay? We didn't get it for an arbitrary pair of modules, so with the help of the Zorn's lemma, we get the surjection for an arbitrary pair of modules. And therefore M star is injective, which I've proven that it was equivalent to M being flat. So what's the largest part of the theorem? Okay? So we can check that a module is flat is the same as the dual being injective, and it's the same thing as IM being this tensor product over R with an ideal. And this is in practice what you use. For flat modules, you use this equality. That is, what is the difference between these two guys? We always have a map from I tensor R to M, which is, I tensor M to M, which is factors. This is over R. The image is always this. The question is, what is the kernel of this map? Okay? And, well, the kernel of anything that is on the kernel of this map is going to destroy this equality. Okay? By definition, the image of this guy is I times M. So what we're saying is that I times M is always equal to this tensor product over R divided by the kernel of this map. And that kernel is having torsion along that ideal. Okay? So now you can think of R being the ring of functions on a space, I being the ideal of functions that are 0 on a subspace, and M being a vector bundle of the whole space. So if you have like this, you have your space, R is functions on that space. You have some subspace, I is the ring of functions that are 0 on this subspace. M is something that lives everywhere, so it's a module over R. So just take a vector bundle over R and take sections of that module, of that vector bundle. So this is an R module, and in particular is an I module. But okay, so what is this saying? The fact that there is some kernel there. It means that this module, if I restrict to this subspace, there's some non-trivial torsion. So for an arbitrary vector bundle, if you give me a section and you multiply by a function, this is never 0. But this statement would say that there are some elements that are 0. So I urge you to think about why this is what you actually use in practice. Well, at least I'm taking a geometric point of view, but it doesn't matter. So all the examples that I did were for rings and even non-commutative rings, and modules were left or right, but not modules on both sides. Okay, so let's continue with something that is going to be more of a philosophical statement, and it's the following theorem. So let's recall something before I gave this theorem. The statement is that if I have a ring and F is a flat module, then this was the definition. Tor n F dot is 0 for n bigger than 0. Particular for projectives are flat, this holds for projectives. So the theorem is you can compute torsion using flat resolutions instead of projective resolutions. Of course, if you take a projective resolution, it is a flat resolution, but there are flats that are not projective. So it's fine to use a flat resolution instead of a projective resolution, and that's easier because there are more flat modules than projective R's. And it gives you the same torsion groups. But more than the theorem itself, I would say that this is much more general. Namely, you can compute any homology theory by using resolutions where the objects that you're resolving by satisfy this thing, that they are acyclic for your homology. So if instead of using here torsion, I had X groups, well, that's not a good example. But for any homology theory that you want, if you look objects such that the higher homologies are 0 are called acyclic, then you can compute your homology by resolving with those objects. So that's more or less the flavor of this theorem. And the proof of this theorem is going to use something very particular about flatness, but that theorem is more general, which I can't really state now. The second thing is, well, why is this useful? Well, for this to be useful, I need, so before proving this theorem, I need to show that there are flat modules that are not projective. And I'll just give you the same example than the book does, but I'll just generalize it a little bit because the book does the Kojoule resolution of a module. So let's produce this. So here, we're going to be looking at this. We're going to grab a field. And I'm going to be looking at the point inside of, so I'm going to be looking at a point inside of A2. So I'm going to be looking at K of x, y as my ring. And I'm going to be looking at an ideal which is generated by x and y. So that's the ideal of functions that are 0 at this point. So of course, if you look at R divided by I, this is just a field. The ring is commutative, and this ideal is a two-sided ideal, so I don't need to worry about like ordering here. But what I want is to get a projective resolution of this. So what I'm going to take is, I'm going to take this projective resolution. So I'm going to take R2, and I'm going to take here wedge 2 of R2, which is isomorphic to R. I'm going to take 0 here. So what are all the maps that I have here? Well, here the map is just so I have two elements in R, and I'm going to send them by multiplication by x and multiplication by y. Okay, so if you have, what you can do here is, if you think of this as a column vector perhaps, AB, then you send it to the multiplication by xy times AB. Oops, I think I've missed my first element in my resolution. This maps to R, and this is the usual quotient. So this map is this map to R. The image of this map is certainly, by definition, the ideal I, which is linear combinations of this form. Okay? So the co-kernel of this map is clearly this, which is the field K. So this map here has as image I, and the kernel of this map is I. So this sequence is exact at this point. That's what we just checked. This is a surjective morphism because it's a quotient, so this sequence is exact at this point. Okay? And all I'm left to tell you is what is the map from here to here. And, well, so what is the kernel of this map? What's the kernel of that map? I want this to be I want it to be exact also at this point, at R2. And I need the image of this guy to be the kernel of this map. So now I need to be careful because I want to get two elements, starting from an alpha here. I want to get two elements such that when I apply this map, I get 0. And this is not so hard. What I can do is multiply it by x, multiply it by y, and put them in a different order with a different sign. So what I can do is, from alpha, I can send it to alpha. Well, I'm going to multiply a by x, so let's put alpha y, and then minus alpha x here. So that when I apply this guy here, I'm going to take alpha xy minus alpha xy. Okay? So the square of this map is 0 here. That's just that composition. The kernel of this map, you can check that it is, well, this is multiplication by a matrix of rank 1. So the kernel is of rank 1, and I'm just giving you one element in the kernel. So it has to be that. Okay. And finally, this map is obviously injective. If my ring doesn't have 0 divisors, this ring is just this polynomial ring. So it's clearly injective. So this guy is also exact here. So we have this sequence. Now this sequence is a general statement, much more general than what I'm describing here. So this sequence of elements in R is called as a regular sequence. What did I use to prove that this sequence here was exact? I've used that I didn't have zero divisors here, that multiplying by y was not 0 here, to check that this map was injected. That multiplying by x is not 0 here. But I've used more. I've used that modulo the image of multiplying by y. So if I want to do this more generally, so let me tell you, a sequence of elements, an ordered sequence of elements, A1 up to AN in a ring R is regular if these AIs are non-zero divisors and so A1 in R, let me call this guy R1, is not a zero divisor. And A2 in R2, which I define it to be R1 divided by the ideal generated by A1, is not a zero divisor. And AK in RK, which I define it to be RK minus 1, divided by AK minus 1, is not a zero divisor. So in this geometric setting, what I have is the plane. If I divide by x, I get the ring of functions on the line. And the remaining ideal gives me the ideal of functions that vanish on the point, which is also not a zero divisor. So these are transverse equations. So the point here is a complete intersection of things, and they are transverse. So I'm not if you do something like this, for example, that's not going to satisfy that. So let's check that. So this is something like saying, well, on Rx, on K of xy, I could look at the ideal of putting y is equal to 0, so that's this line. Or I could look at the ideal of putting this guy is equal to 0, so that's y minus x squared. Now, this thing here is not a regular sequence. Because if I divide by this guy first, right, so if I choose them in this order, then whenever I see a y, I just put an x squared. But then y is x squared. So this quotient like this is when you take the first quotient, you're going to get something like k of x divided by x squared, and x, or k of y divided by y squared. And y is not a zero divisor here. Okay. So whenever you have a regular sequence inside of a ring, then you get a module, which is Rn. Oops, I keep using that letter R. Shoot. OK, I'm going to need to be fast. So you have this Rn, which is this module has as basis these guys, 2R. So this takes alpha 1 up to alpha n, and you map it to A1, AN, times that guy, alpha 1, alpha n. And of course, the quotient, the image is just the ideal generated by all of these AIs. So this maps to like this. This guy is surjective. And here I is the ideal generated by all these elements, A1 up to AN. And you can extend this by putting here. So I can view this as wedge 1 of Rn to wedge 2 of Rn, and so forth. Wedge n of Rn, and this is isomorphic to R. So there's a unique way of extending this. The extension is just playing the same game here from n minus 1 forms, well, from n plus 1 forms to n minus 1 forms of putting alternating signs. So for that, I'll leave you as an exercise. Write this. Write this example. But instead of using alpha, use alpha to be of the form beta wedge gamma. If you write the differential, when you think of this alpha as the wedge product of two guys, here I've used that this wedge product of two guys was the same as R. Wedge 2 of R2 was the same as R. But if you write this alpha as the wedge product of two guys in R2, then this differential becomes more natural and easier to write. So once you do this, so here beta and gamma are in R2, not in R. So once you do this, then it's easy to figure out what this extension is. So this is the Koszul complex. This is known as the Koszul resolution. Koszul resolution of R divided by I. And this is what you do if you want to compute, say, the Durham complex of a smooth variety that is given as the zeros of a bunch of equations. Okay, so that was a caveat just to say how this sequence came from. This was very general. But I claim that that ideal is flat and is not projective. So, well, we have this sequence. And this is a projective resolution of R mod I. Right? So we have R on the first term, R squared on the second one, and wedge 2 of R in the third one. So that sequence is a projective resolution. 0, R, R squared, R is a projective resolution of this guy. And what I'm going to do is I'm going to just take the tor of that with I. Just take tor over R with of this thing n of this thing with I or even with k. So you can do this, or you can just take the tensor product over with I. Okay, so for that, we just tensor these things with I, and you see that these ideals, that these differentials become 0. Yeah, so I won't have time to finish in order to prove to you this theorem. Yeah, so I think I'm just going to pick up here next time with this example, and then I'm going to prove this, and I'll continue with X groups.